In this video, I will talk about using hierarchical clustering and k-means clustering to measure similarities between observations and segment them into similar groups. Cluster analysis is a type of descriptive data mining methods, which is also called unsupervised learning techniques. So in an unsupervised learning application, we don't have outcome variables to predict. Rather, the goal is to use the variable values to identify relationship between the observations. Unsupervised learning approach can be thought of high-dimensional. High-dimensional descriptive analytics are designed to describe patterns and relationships in large data sets, especially one that has many observations of many variables. Since we don't have an explicit or no outcome in unsupervised learning, we usually do not have definite measures of accuracy. So instead, we will use qualitative assessments. For example, how well the results match human experts' judgment. So we use that to evaluate and compare the results from an unsupervised learning method. So the goal of clustering is to segment observations into similar groups based on the observed variables. Clustering can be used during data preparation to identify variables or observations that can be aggregated or can be removed for consideration. So for example, in the text mining project, we used LDA topic modeling algorithm to successfully separate Yelp reviews in French from all the English-based reviews, so we can remove them from our analysis. Cluster analysis can also be used to identify outliers, so which in a manufacturing setting, it may represent quality control problems, and in financial transactions situation, it may represent fraudulent activity. So cluster analysis is commonly used in marketing also to divide consumers into different homogeneous groups, which is a process known as a market segmentation. Identifying different clusters of consumers allows a company to tailor the marketing strategies for each segment. So there are two clustering methods. The first method is the hierarchical clustering. It starts with each observation belonging to its own cluster, and then sequentially it merges the most similar cluster to create a series of nested clusters. So that's why it's also called the bottom-up approach. The second method, the k-means clustering, assigns each observation to one of the k clusters, making sure that the observations assigned to the same cluster are as similar as possible. So both methods depend on how observations are similar. So let's see how we measure similarities between observations. The goal of cluster analysis is to group observation into clusters so that the observations in a cluster are similar and observations in a different cluster are dissimilar. So we need to measure similarity, or the other way around, the dissimilarity. Some metrics check similarity between observations, and a clustering method uses this kind of metric would try to maximize the similarity between observations. Some other metrics measure dissimilarity or distance between the observations. And a clustering method using one of these metrics would try to minimize the distance between observations in a cluster. When observations include numerical variables, we usually use Euclidean distance as the method to measure dissimilarity between observations. Let observations U and V each comprise the measurements of Q variables. So then the Euclidean distance between observations U and V is the square root of the sum of the square of the difference of U and V for each variable. In math, the Euclidean distance formula is used to find the length of a line segment given 2 points on the plane. So this figure shows Euclidean distance for 2 observations consists of 2 variable measurements. First variable in the x-axis and second variable in the y-axis. Euclidean distance becomes smaller as a pair of observations become more similar with respect to their variable values. Here we have a KTC dataset as an example. KTC is a financial advising company that provides personalized financial advice to its clients. The company would like to segment its customers into several groups so that the customers within the group are similar and dissimilar with other groups, so then KTC can probably create some customized marketing campaign to each of the segments. For each customer, KTC has an observation of 7 variables: age, female, income, married, children, car loan, and mortgage. So, for example, the observation U equal to 61,057,881,1200 in that order correspond to a 61-year-old male with an annual income of $57,881 and married with 2 children but no car loan and no mortgage. So as you can see here, we have a mix of numerical and categorical variables here. Can you spot on which ones are the categorical variables? That's right, it's female. It's 1 if it's female, 0 if not female. And married, loan, and mortgage. So we say that they're categorical because they have a value of either 1 or 0. So it's Boolean value. So Euclidean distance is highly influential by the scale on which the variables are measured. For example, on the test of clustering customers of KTC based on the variables age and income, let the observation U correspond to a 23-year-old customer with an annual income of $20,375, and the second observation V correspond to a 36-year-old with an annual income of $19,475. As measured by the Euclidean distance, the similarity between these 2 observations is 901. So we can see that when using the raw variable values, the amount of dissimilarities between observations is dominated by the income variable because of difference in the magnitude of the measurements, as income is a lot larger than age by nature. Therefore, it's common to standardize the units of each variable j of each observation u, that is uj, and the values of variable j in the observation u is replaced with a z-score, zj. The standardized or normalized value of observations u and v are negative 1.76 and negative 0.56 and negative 1.76 and negative 0.62. The dissimilarity between these 2 observations based on the standardized value is 0.998. And based on the standardized variable values, we observe that the observations U and V are actually much more different in the age, 0.994, than in the income, 0.004. So when we use Euclidean distance, we usually will standardize our data set, especially when we have variables that are significantly different in the unit measurements. The conversion to z-scores also make it easier to identify outlier measurements, because outliers can distort the Euclidean distance between observations. After conversion to z-scores, unequal weighing of variables can also be considered by multiplying the variables of each observation by a selected set of weights. So for example, after standardizing the units on customer observations so that income and age are expressed as their respective z-scores, instead of expressed in dollars and years, we can multiply the income z-scores by 2 if we wish to treat income with twice the importance of age. So that 2 would be the weight, right? So in other words, standardizing removes bias due to the difference in measurement units, and variable weighting allows us to introduce appropriate bias based on the business context. When clustering observations only on the base of categorical variables, and which are coded as 0 or 1, or what we call dummy variables, a better measure of similarity between the two categorical observations can be done by counting the number of variables with matching values. So the simplest overlap measure is called the matching coefficient, and it's computed like this formula, which is the number of variables with matching values for observations U and V divided by total number of variables. One weakness of the matching coefficient is that if two observations both have a 0 entry for a categorical variable, this is counted as a sign of similarity between the two observations. However, in real life, matching 0 entries do not necessarily imply similarity. So for example, if the categorical variable is own a minivan, then a 0 entry in two different observations, like two customers, does not mean that these two people owns the same type of car, but rather it just means that neither of these two people owns a minivan. So to avoid misstating similarity due to the absence of a feature, a similarity measure called Jacob's coefficient does not count matching 0 entries. So it's computed like this formula. Number of variables with matching non-zero for observations U and V divided by total number of variables, subtract number of variables with matching 0 values for observations U and V. So for 5 customer observations from the KTC dataset, this table contains observation of the categorical variables female, married, loan, and mortgage. And based on the matching coefficient, observation 1 and 4 are more similar, 0.75, than observation 2 and 3, 0.5. Because 3 out of 4 variables value match between the observation 1 and 4, right? Between 1 and 4. Just 2 matching values out of 4 for observation 2 and observation 3. Observation 2 and observation 3. So however, based on Jacob's coefficient, observation 1 and 4 are equally similar. 1 and 4 are equally similar with 2 and 3. Both are at 0.5. That's because Jacob's coefficient doesn't count the matching 0 values for loan and mortgage variables for observation 1 and observation 4. So in the context of this example, choice of matching coefficient or Jacob's coefficient depends on whether KTC believes that matching 0 entries implies similarities or not. There are 2 clustering approaches. The first one is the hierarchical clustering approach that starts with each observation in its own cluster and then iteratively combines the 2 clusters that are the most similar into a single cluster. So at each iteration, the algorithm increases the level of aggregation by decreasing the number of distinct clusters. Hierarchical clustering determines the similarity of 2 clusters by considering the similarity between the observations composing either cluster. So there are several methods for measuring similarity between clusters. We've learned several ways of measuring similarities between observations, including Euclidean distance, matching coefficients, or Jacob's coefficients. With one of these methods of measuring similarities between observations, there are also several hierarchical clustering methods alternative for comparing observation in 2 clusters so that we can obtain a cluster similarity. Using the Euclidean distance to show how similarity can be measured, So this figure shows a two-dimensional illustration of 4 methods, including the single linkage, complete linkage, group average linkage, and centroid linkage. When using the single linkage clustering method, the similarity between the two clusters is defined by the pair of observations, one from each cluster, that are the most similar. So they're the closest. So the single linkage will consider two clusters to be close if an observation in one of the clusters is close to at least one observation in the other cluster. However, the cluster formed by merging two clusters that are close with respect to single linkage may consist of a pair of observations that are very different. The reason is that it doesn't consider how different an observation may be from other observation in the other cluster, as long as it's similar to at least one observation in that cluster. In 2 dimensions or variables, single linkage clustering can result in long extent clusters rather than compact circular clusters. Now, the complete linkage clustering methods is almost the opposite of the single linkage, right? So it defines the similarity between the two clusters as the similarity as the pair of observations, one from each cluster. So they're the furthest from each other. So complete linkage will consider two clusters to be close if their most different pair of observations are close. This method produces clusters such as that all members' observations of a cluster are relatively close to each other, right? And the cluster produced by complete linkage have approximately equal diameters. However, the clustering created with the complete linkage can be distorted by outlier observations, because you can see that if you have an outlier somewhere out there further, and then the distance between the two most different pair will be very long, right? So far, you notice that the single linkage and the complete linkage method define between cluster similarity based on the single pair of observations in two different clusters, either most similar or least similar. So in contrast, the group average linkage clustering method defines the similarity between the two clusters as the average similarity computed over all pairs of observations between the two clusters. If cluster 1 consists of n1 observations and cluster 2 consists of n2 observations, the similarity between the two clusters would be the average of similarity measures. This method produces clusters that are less dominated by the similarity between the single pair of observation. The median linkage method is similar to the group average linkage, except that it uses the median instead of the mean of the similarities computed between all pairs of observations between two clusters. The use of median usually reduces the effect of outliers. So if you have like large range of values in your data set for a particular variable, you probably want to try using median to reduce the bias. Lastly, centroid linkage uses the averaging concept of cluster centroids to define between cluster similarities. The centroid for cluster K or like CK and is found to by calculated the average value for each variable across all observations in a cluster. So in other words, a centroid is the average observation of a cluster. The similarities between cluster K and cluster I is the similarity of the centroid CK and CI, or C1 and C2 in here. There are two other methods for merging two clusters. Ward's method merges two clusters in a way that the similarity of the observation within the resulting single cluster increases as little as possible. It tends to create clearly defined clusters, and they're often similar size. For a pair of clusters under consideration for aggregation, Ward's method computes the centroid of the resulting merged cluster and then calculate the sum of the square dissimilarities between the centroid and each observation in the two clusters combined. So representing the observations within the cluster with the centroid is considered as a loss of information, because the individual difference in these observations will not be captured by the cluster centroid, because you take the average, right? So hierarchical clustering using Ward's method results in a sequence of aggregated clusters that minimize the loss of information between the individual observation level and the cluster central level. So the other method is the McQuitty's method, which merges two clusters A and B. The similarity of the resulting cluster AB to any other cluster C is calculated as dissimilarity between A and C plus dissimilarity between B and C divided by 2. So at each step, this method then merges the pair of the clusters that results in a minimum increase in the total dissimilarities between the new merged cluster and all the other clusters. So returning to our KTC example, we are interested in developing customer segments based on gender, marital status, and whether the customer is paying a car loan and a mortgage. So using this data set, we can base the clusters on a collection of categorical variables, including whether the customer is female or not, whether it's married or not, whether he has a loan or a mortgage or not. So they have the values of zeros and ones. They're categorical variables. So in another video in my channel, I demonstrate how to use analytic solver to conduct hierarchical clustering for this data set, where I use the matching coefficient to measure similarity between the observations and the group average linkage method to measure similarity between clusters. So the choice of the matching coefficient over Jacob's coefficient is reasonable because the pair of customers that both have an entry of 0 for any of the 4 variables here imply some degrees of similarity. So for example, 2 customers that both have 0 entries for mortgage means that neither have significant debt associated with a mortgage. So this figure shows a dendrogram to visually summarize the output from a hierarchical clustering using the matching coefficient to measure the similarity between observations, and using the group average linkage clustering method to measure similarity between clusters. Okay, so again, you can create this dendrogram using the analytic solver or Python or other data mining softwares. A dendrogram is a chart that illustrates the set of nested clusters resulting at each steps of aggregation. The horizontal axis of the dendrogram lists the observation indexes. The vertical axis of the dendrogram represents the dissimilarity or distance resulting from a merger of 2 different groups of observations. Each blue horizontal line in the dendrogram represents a merger of 2 or more clusters, where observations in the merged clusters are connected to the blue horizontal line with a blue vertical line. For example, the blue horizontal line connecting the observations 4, 5, 6, 11, 19, and 20A basically shows that the 6 observations are grouped together and the resulting cluster has a dissimilarity measure of 0. Because the 6 observations represent 6 customers have identical values for the female, married, loan, mortgage, right? So in this case, each of the 6 observations correspond to a married female with no car loan and no mortgage in here. So following the blue vertical line up from the cluster 4, 5, 6, 11, 19, and 28, another blue horizontal line connects this cluster with the cluster consisting only the observation 1. So therefore, the cluster 4, 5, 6, 11, 19, 28, and the cluster 1 are merged, resulting in the dissimilarities of 0.25. You can kind of see it in here. So the dissimilarity of 0.25 results from this merger because observation 1 differs in 1 out of the 4 categorical variables. Observation 1 is an unmarried female with no car loan and no mortgage. Whereas in here, all these customers are married. So that creates the difference when you merge the two groups together. To interpret a dendrogram at a specific level of aggregation, it's helpful to visualize a horizontal line, such as one of the black dashed lines that we have drawn across in here, and the bottom horizontal black dashed line interacts with the vertical branches in the dendrogram 3 times, right? 1, 2, and 3. So each intersection corresponds to a cluster containing the observations connected by the vertical branch that is intersected. So we can see that the cluster 1 includes the observation 4, 5, 6, 11, 19, 28, 1, 7, 21, 22, 23, 30, 13, 17, 18, 15, and 27. This is one cluster if we are crossing the black dotted line in here, one cluster. And the next cluster is smaller. It has only 2, 26, 8, 10, 20, and 25. This is the second cluster. And the third cluster is also small. It has 3, 9, observation 14, 16, 12, 24, and 29. So cluster 1 are mix of males and females. 15 out of 17 married, no car loans, 5 out of 17 with mortgages. And cluster 2 contains all males with car loans, 5 out of 6 married, and 2 out of 6 with mortgages. And finally, cluster 3, all females with car loans, 4 out of 7 married, and 5 out of 7 with mortgages. So you can interpret each of the clusters, and they're like different, have different focus, right? So the nested construction of the hierarchical cluster allows KDC to identify different numbers of clusters and assess the implications. The sliding up of the position of the top horizontal black line will result in merging the cluster 2 with cluster 3 with a single more dissimilar cluster. The point of agglomeration is called the cost of merging cluster in terms of decreased homogeneity within clusters. In other words, every time you merge 2 clusters together, you kind of compromise on the similarity. You introduce more differences. So that's the cost. So therefore, vertically extended portion of the dendrogram represent the mergers of more dissimilarity of clusters. The longer the line is for the merge, and the more cost it is. On the contrary, vertically compact portion of the dendrogram represents mergers of more similar clusters. So you will kind of want to keep the lines kind of short between the merge of the clusters. So if you find the largest gap between the 2 nearest height clusters, in this case, this is the gap, right? So between merging this and that, you have this much cost to absorb. So this is the largest compared to others. Those are smaller, right? So you stop in here. So this, you have 1, 2, and 3 clusters, and you stop in here. So, and then you can go ahead and interpret each of the 3 clusters, and hopefully that will also make sense put into business context. So another concept is the cluster's durability. A cluster's durability or strength can be measured by the difference between the distance value at which a cluster is originally formed and the distance value at which is merged with another cluster. So in this figure, we can see that the cluster consisting of 12, 14, and 29, which means single female with car loans and mortgages, is a very durable cluster because the vertical line, look how long the vertical line is in here for it to end before it merges with another cluster, this cluster next to it. So this line is very long, so therefore we say that this cluster is most durable or strongest. Another clustering technique is the K-means clustering. In K-means clustering, the analyst must specify the number of the clusters K. And if the number of clusters K is not clearly established by the context of the business, then the K-means clustering can be repeated for several different values of K and then compare the results. So usually we will try the k from 2 to 10, right? And give a value of k. The k-means algorithm randomly assigns each observation to one of the k clusters. And then after all observations have been assigned to a cluster, the resulting cluster centroids then are calculated. And this cluster centroids are basically the means of k-means clustering, right? So using the updated cluster centroids, all observations are reassigned to the cluster with the closest centroid using Euclidean distance. So yes, k-means clustering use Euclidean distance. So the algorithm repeats this process, which is the first calculate cluster centroids and then assign each observation to the cluster with the nearest centroid until there is no change in the clusters or specified maximum number of iteration k is reached. So as an unsupervised learning technique, class analysis like k-means or hierarchical doesn't have any explicit measure of accuracy. So you can't say that, oh, here's the accuracy of 90% I tried to hit. So then what is considered to be a good clustering is very subjective. So it kind of depends on if the analysis can interpret the cluster results, right, in meaningful, insightful kind of way in the business context. So regardless, one can measure the strength of a cluster by comparing the average distance in the cluster to the distance between cluster centroids. So one rule of thumb is that the ratio of between cluster distance as measured by the distance between cluster centroids to average within cluster distance should exceed 1 for useful clusters. So in other words, you will want the between cluster distance to be larger than the within cluster distance, right? So you want the observations within a cluster to be more closer to each other, and you want the observation in other clusters to be more further away as possible. So this figure shows an example of k-means clustering using KDC dataset. So here we're doing 3 means clustering, meaning that k equals to 3, right? So you see 3 clusters. So it's based upon the customer income and customer age. So cluster 1 is characterized by relative younger, lower income customers, and with the circles are the centroids. So cluster 2 is characterized by relative older in age and higher income customers, and cluster 3 is characterized by relative older and lower income customers. Notice that although this figure is plotted in the original scale of the variables, the clustering was actually based on the variables after standardizing or normalizing their values. This table shows the cluster 2 is the smallest with only 8 observations in it, but most heterogeneous because the average distance between the observation is 0.739, which is the largest among the 3 clusters. We can also see that cluster 1 is the largest cluster because there are 12 observations in it, which is the largest among the 3 clusters. And cluster 3 are the most homogeneous cluster because the distance between the observation in cluster is 0.52, which is the smallest among the 3 clusters. So this table displays the distance between each pair of the cluster centroid to demonstrate how different the clusters are from each other. In general, the larger the ratio of the distance between a pair of cluster centroids and the average within cluster distance, the more distinct the clustering is for the observations in 2 clusters in the pair. The better it is, right? You have to figure out whether the clusters can be interpreted, can be meaningful, using the ratios of the between cluster distance and average within cluster distance provide some guidance in determining k, which is the number of clusters. The best case should make the maximum between cluster distance or minimum within cluster distance. So if you have a small data set, let's say fewer than 500 observations and want to easily examine solutions with increasing number of clusters, then you may want to use the hierarchical clustering. And hierarchical clusters are also convenient if you want to observe how clusters are nested. However, hierarchical clustering can be very sensitive to outliers, and the clusters may change drastically if observations are eliminated from the dataset or added to the dataset. It also has a lot of computing overhead, so for a large dataset, it runs really slow, and you probably want to try the k-means clustering. If you know how many clusters you want and you have a larger data set, such as more than 500 observations, you may choose to use the k-means clustering. And remember that k-means clustering partitions the observations. So it's appropriate if you're trying to summarize the data with k-average observations that describe data with a minimum amount of error. However, because Euclidean distance is the standard metrics for k-means clustering, and it's generally not appropriate for categorical data or binary or ordinal data, because in those cases an average is not really that meaningful. Next, I would talk about how to find the best k using a couple methods that you can manually calculate or using the results from Analytic Solver. I also covered that in my Analytic Solver demonstration video. So there are two approaches that you can find out the best k for k-means clustering. The first one is to use the minimum sum of within cluster distance. So with software like RapidMiner, with data mining software like RapidMiner, you can build process log to output, or with Python, you can call library code to output total within cluster sum of squares, or WSS, and elbow chart. So however, in Analytic Solver, there's no direct results for that. So instead, you will have to calculate manually, and you can do that. So for example, in the case of k equal to 3, so the total WSS equal to sum of the square of bracket 1. So in other words, you calculate the total WSS, taking that value to the power of 2 and plus the next one to the power of 2, and so on. And now you can see that you can automate somehow to calculate the WSS by using if function in the Excel. And then you can compare the WSS for different k. This is just for k equal to 3. So the second approach is to use the maximum average inter-cluster distance. And this is recommended if you have Analytic Solver. So what makes this approach easier is that Analytic Solver provides the inter-cluster distance. So that is the distance between each cluster centroid in kind of like the underscore output worksheet. So if we use inter-cluster distance, then we can focus on finding the k that maximize the distance between the clusters. So for example, when k equal to 2, you run in Analytic Solver, you're going to get this table, right? So you have two clusters, and those are the inter-cluster distance. And then you can calculate the average inter-cluster distance is how much, right? And then when k equal to 3, and then you just like add them all up and divide it by 6 pairs, right? So it's like so even though the k equal to 5 have a higher distance, k equals 3 is still the best. Why? Because when we see that the k equal to 4, the distance actually goes down. So that could be an indication of the elbow if you graph this. And so adding extra cluster is not worth the costs. So we stop at 3 clusters.